We have to talk about concepts. And recently I gave a talk in the Back to Basic tracks of the CPPCon, and one of the basics was CPP concepts introduced in C++20, which was a little bit funny, but I see the reason. And the reason is, I think we are all sure now in the standard committee, as well as in most of the community, that concepts are a huge step forward in generic programming. So this talk will explain you a little bit why and introduce the most important things you have to know. And if you are interested in more, well, there's enough out, like books, talks, trainings in 2 weeks from meeting C++, and so on. So, good. Let's assume you write a generic function. The generic function wants to insert a value into a collection, a value of type t into a collection of type call t. And as you see here inside, we call pushback to insert the value. This works fine when we insert an int into a vector of int. This does not work if we insert an int in a set, because a set does not support pushback. So you have to do something else. And a very naive approach would be to say, well, let's add another add function template. So another add function template takes a value, inserts it into a collection, calling insert. But that doesn't work, because what the compiler sees here is 2 implementations of the same function template, 2 different implementations, and that's not allowed. So the compiler will say, I have no idea which one to call. That's not valid code. And it will not compile. So the way we handled that before C++20 was kind of, let's see, strange abuse of template magic code called enable if and spinne. But it turned out that we need that. We need a solution for this, an easy solution all the time. So we came up with a language feature in C++20, which is called concepts. And here's how you solve this problem with that. You need simply in one of these function templates an additional line saying there's a requirement. Well, I use here the keyword requires. It's not a requirement, it's a constraint. It constrains the visibility, the usability of this code. And it says, this add can only be called if call t supports pushback. What you see on the right is what we call a concept. And here's how it is defined. The concept says, if there's a type called call t, it satisfies has pushback if the following requirements in the dark gray area on the right are valid code. The thing on the right has to be valid, and you have to read it the following way. Assume I have an object C of type call t, and assume I have an object V of value type of call t, is then the call of pushback with V into C valid or not? You could do that before using declval to say, assume I have an object, and using static asserts and a couple of other things, and spinne and so on, but it looked tremendously ugly. So this is a very clear readable code. You formulate on the right requirements, could be multiple. In fact, we have here multiple requirements. One requirement is that call t has a member value type, and the other is that pushback is supported, provided you have a value of the value type and a collection of the collection type. Then we give it a name, and concepts are named requirements. So a concept is just for one or multiple requirements a name so that we can handle these different requirements by one thing. And that one thing is then used to constrain the first add function template. To say, let's only allow to use this template. This template is only visible if this constraint is satisfied or met. This solves the problem. So surprisingly, you might say, wait a minute, don't we need another similar thing, the second add function template? No, we don't. Because what happens now is, if we add a vector, int, to a vector, as in the first add statement, for the compiler finds two add function templates. Both are valid for vectors. The first one is valid because vectors have and support pushback. And the second one is valid because it's always valid for all types. I mean, there's no restriction, no constraint. So for a vector, both is there, but this is no longer the same function template. These are two different function templates. And the rule that applies here says, if there is one function template more constrained than the other, then the more special one wins, as we already have in function templates even before this with partial specialization and so on. So therefore, it works now. That's it. Look at the green area here. We have introduced two template parameters, and then we have defined a constraint on one of the template parameters, on the first one. You can write it differently. There's a different syntax for that, and it says, yeah, let's directly constrain the first template parameter with the concept. That's something only concepts can do. There's nothing else you can use here. So for some type call T that has pushback and some other type T, here's the add function. And this add function is still more special than the other add function template because it has the constraint. That's it. Well, new feature means new bugs. So if you understand what I taught you here in the first 5 minutes, you might understand what happens here now. Let's make a mistake. And let's, in the requirements for has pushback, misspell pushback. So let's skip the underscore. So what we say here is the concept has pushback is satisfied if there's a member function called pushback without an underscore. So what is the result of this? What happens now if you compile this? Well, as usual, error messages in C++ are great to help you there. That's it. Wait a minute, what? So the complaint is, when I insert an int into a vector of int with that, the error message is, I cannot call insert. Huh? Yes, you should not call insert, you should call pushback. But, I mean, that's exactly what's going on here. The problem is, the first add is not valid for a vector because it's only valid for a vector that has pushback without an underscore. So the first add cannot be used. So the second add is used. And that means that we try to compile the second add for a vector, and that fails because insert is not supported. Woo, okay. How do I know that my concept works? Well, how do you know that code works? Testing, yes. You test. How do you test the concept? Well, you have to know something to see how it works. It's pretty easy to do that. The point is, requirements and concepts are compile-time Boolean values. So how do you test the concept? The concept is true if the concept is satisfied. So the requirement is met. All the code there specified is valid. All the constraints that are satisfied are valid. So you can simply use a static assert, because that's a way to check at compile time whether a Boolean value is true or false. So this checks and makes sure that has pushback for a vector of int is satisfied, while has pushback for a set of int is not satisfied because there's a not in front of has pushback. It's that easy. Good. Well, in C++20, we came up with a couple of new features, and there's another nice feature that simplifies the writing of generic code tremendously, which is instead of using template parameters, you can use auto now, even in ordinary functions. But these are no ordinary functions anymore. This is not an ordinary function. This is just another way to write a function template. So this is what we call an abbreviated way to write a function template. It's equivalent to writing the exact function template as you see it on the right, with one difference. On the right, you have names for T1 and T2. On the left, you don't have names for them. Everything else is the same. So the implementation belongs in the header file, but because it's a function template, no inline is necessary. And you could explicitly specify 1 or 2 template parameters. That's also supported. Weird things happen, by the way, if you mix name templates with auto, but we don't talk about that here. Okay, we run, as it is just another syntax, kind of another syntax at least, we run into the same problems. So if we want to overload that for calling pushback and insert, that doesn't work. Just from looking at the signature, this is 2 definitions of the same function template, so that's not allowed. So the solution is constrain one of them, at least. Here's how you do that. Has pushback is a concept you apply to auto. As you can apply a concept to a template parameter, you can apply a concept to auto. Again, it's the only thing you can apply to auto. Concepts are the only thing you can apply there. And you have seen the definition of has pushback already, and that is, as you see it here on the top. Okay. Now, an interesting question might come up, which is, can I also, instead of directly applying a concept to auto, can I use it in a requires clause? Well, we have requirements, we have a concept, we have type constraints. So can I switch to this? Think about it. Think about it. You get an error message. Why? The error message is interesting. Again, the error is I cannot call insert to add an int to a vector of int. That's a clear proof that the first add is not used. So that's the first thing you have to understand. So if you ask, why the hell do they call insert? Yeah, because they call the wrong add. So why is that? Because the first add, which is more specialized, more special, is not used. So that means a requirement is not satisfied. The concept is not satisfied. But why? Hey, auto, reference, call, decal type of call, that's a type of call. What's the problem? It's maybe about constant? No, it's not always const fault. What is a decal type of call? A reference. Yes. So we did constrain auto. Auto is not a reference. The auto ref is a type of call. So what you pass here to has pushback is the type std vector of int reference. And now the question is for this type, the requirement satisfied on the top right? And the answer is no. Why? Because references have no members. So there, the problem is on the top right, the declaration of call t : value type. You, in this example, try to compile or check whether it's valid that you can have a value type for a reference to a vector of int, which is not valid. So you don't get an error message that's not valid. Your concept is not satisfied. So that concept is not used, so the other add is used. Got it? Good. How do we fix that? Well, one way to fix that is to say, well, if we take the decal type of the collection, let's remove referenceness. In general, you always often pass const references, so you might also remove constness and referenceness to get the pure type. There's a new type trait for that introduced in C++20, which is called remove CVRef, const, volatile, and referenceness, which replaces to some extent std decay, which we took for that as a workaround before. It's not necessary here because remove reference is enough in this case. But could we have come up with a solution where the concept is not a problem, does not have a problem with references? Yes, you can write it that way. You can say, my concept is satisfied if when I remove from the pass type its reference and constness, there is a value type, and that element, that value type, can be pushed back into the container. So if you write it that way, then suddenly has pushback of a decal type of collection works. When you design concepts, it's a good idea to think about when should this concept work and when not. Or in other words, one test case is, what happens if I pass a reference to this concept? Okay? There are other ways to do that, by the way. There's a new helper function called give me the value type of the range, and this helper function is a new utility in the ranges library, and that even works for references. So you could also use that. That utility even works for raw arrays, which is not possible to do here because you cannot call pushback or insert for a raw array. But in general, so this helper function is a little bit more robust than this lower assembler kind of type trait usage here. Good. Well, but there's another way we can do that. Well, at the end, we don't want to know if the container supports pushback. We want to know, can I insert an element of this type into the collection, and the type could be different. So we can also come up with a different solution saying, my requirement is, can I push back a T in a call T? So now we have a constraint for multiple template parameters. And here's the definition. It's a concept, 2 template parameters. The requirements is, assume I have an object C of type call T, an object V of type T. Can I push that back that? That's it. And by the way, that also works for decl type of call without removing referenceness, because a declaration in the requires clause just creates an object of this type, a value object. It doesn't matter whether the type is a reference or not. C is an L value, and that's always valid code here. Don't do that. Well, all I taught you so far, don't do that. This was to explain you concepts, the basics of concepts. But don't do that. Don't introduce a concept for each and everything you want to do with an object. Because your function templates will not call only pushback. They will call empty, they will compare, they will iterate, they will do a lot of things in your generic code. So you would have to write a requirement saying, I require this and this and this and this and this and this and this. You reveal the implementation details into the signature. And this, by the way, as this is all a compile time feature, we have to find out which part of our code compiles or not. This takes compile time. It does not take runtime. So don't write concepts that fine-grained as I used here to introduce the principles. That might be a good approach. You might say, oh, let's introduce a more general purpose concept that in general says, is it a sequence container? Is it a container where the elements are stored one after the other, where Q can specify, I want to have this element in the front or in the back, so you specify the location, the position of an element. And here's how we specify this concept. And you might see here, and you see again that this is a compile time Boolean value, a concept. We start in the specification of saying, well, it has to be a range. That's a standard concept that requires, can we iterate over the elements? Or we require that we can iterate over the elements. And then we have a couple of additional requirements, which is we can push back a value, we can pop back a value, we can insert a value with an iterator, we can erase a value with an iterator, we can clear all the values, we can create a new container initialized with a couple of values or assign a couple of values. We can compare a container with another and see whether the outcome is convertible to the bool. So you see on the right the detailed syntax, or part of the detailed syntax that is supported and possible to use when defining concepts. Especially the last one, the last item there might be interesting. You might say, why is it good to compare myself with myself? This is a compile time check, not a runtime check. You don't care about values and which collection it is. It's just a question, can we compare an object of this type with another object of this type calling less than? And this is test case. This is not asking for, is there an operator less than defined? This is, would this compile? So in C++20, we start to implement comparisons with the spaceship operator. So that's the way this might be supported. So the only question is there any way that I can compare a sequence container of type call T with another sequence container of type call T, and the result is usable as a bool? That is what we test here. And that is what a concept you could use in a couple of different places. We don't have that concept in the standard library, by the way, but kind of other concept like this we have in the standard library. There's an interesting thing here you can see when we look at this definition, which is look at STD ranges range of call T. So the first thing we say, we come up with a couple of special things, and call T should be a range. So we use here a standard concept. So first of all, the standard library provides standard concepts. Then, how do they do that? Let's look. That's how the C++ standard specifies the concept STD ranges range. Yes, they have their own namespace for some reasons. And again, you see the concept range is satisfied when you assume you have an object of type T. You can call for this T a helper function STD rangeless begin and a helper function STD rangeless end. So, which roughly says you can call begin and end for this thing, which is the basics for normal iterations. But why don't we call a member function of T? Why don't we say T.begin? Because this utility, it's again a utility, checks a couple of things. It checks, is there a member function, begin? Or is there a freestanding function where we can pass T as an argument called begin? Or is it a raw array? Then begin of T is T plus 0. So the address of the first element. So again, makes sure that the concept range, for example, is also satisfied for raw arrays. But there's more. What we say, we will, in the definition of these helper function, there's a requirement that this T is not a temporary object, so an R value, because we would get begin for an object, and then afterward the object is gone. So it's not a good idea to use that object in any way. And there's even more in this concept. So let me open the whole definition of this concept, and there's text. Yes, there's text. And that text tells a few other things, requires a few other things. So we, in addition, say T models STD ranges range only if begin and end denote a range. That's what we say there is. Begin and end have to refer to the same object, and begin has to be in front of the end. So otherwise, it's undefined behavior. That's, by the way, nothing a compiler can test. This is a runtime specification specified in the concept. And the others are also things a compiler cannot test. We say, well, begin and end must be reasonable, cheap. I don't explain that here. And non-modifying. So begin should never modify anything. That's again, nothing we can test. You could say by looking at, is it const, and make some assumptions. But even if it's not const, the question is, does it change or not? Does it modify or not? No, we say, if it does modify, then this concept is not met. But guess what? Your test case will say it met. Because that's nothing a compiler can check. So you see here that concepts not only specify testable behavior, they also specify semantic or runtime requirements which cannot be checked by compilers and to some extent are just documentation. Documentation in two ways. You should make sure that if you have something that looks like a range, so something that provides begin and end, that should be met. And in another way, that if somebody says, I require a range, I can assume that this is met. But it's easy to violate this. Okay, so we learned concepts also check runtime and semantic aspects of behavior. Let's come back to this example. So we learned you should not do that to have a single requirement for can push back or has push back or whatsoever. Don't do that. It's too fine-grained. So what can you do instead? Well, this on the top is what we call a requirement expression. The keyword requires is used to specify one or multiple requirements. What we see in the blue box is a requirement clause, a requires clause, excuse me. That is something to constrain generic code. So where we usually apply a concept or requirements. And you learn that requirements and concepts are compile-time Boolean values, which means that the requires clause checks compile-time Boolean values. So here's a way to skip defining a concept for that. You could say, OK, my first add requires, as a constraint, that the requirement that I call pushback for the value to put it into a collection is satisfied. Twice the keyword requires. Looks ugly, but works. Which is better than looking cool and creates confusion, like universal references in C++. But there's more. It's a compile-time Boolean value. So you can combine these two add functions and merge them into one. Because we only have introduced them to be able to distinguish between how to insert the value with pushback or insert. So we write one function template, and then we use a compile-time if, introduced in C++ 17, to say, well, if the concept can pushback is satisfied, then we call pushback, otherwise we call that. But again, it's not necessary to introduce a concept here. You can write it that way. Everybody who writes non-trivial generic code sooner or later wants to have something like, oh, I wish I could write, if that's supported, do that, otherwise do that. We have it now. It's, you write requirements as a condition in a compile-time if, and depending on these requirements, and it could be multiple, combined with and, you do this or that in the function body. Can we that way also switch between different signatures? We come to that. Before we come to that, let's look at another benefit of concepts, which is it's not only to select and choose for the right function template, it's also to improve error handling. So here you see it, that we change the definition of the set, where we insert 42, to say it's a set of string. That's not good. We cannot insert an int in a set of string. And I think if you're a little bit programming with C++, you all know the horrifying, terrifying error message of broken template code. Somewhere in the deep darkness of your code, you get an error message that, I don't know, in line 518 of SDL-set.h, there is something broken. And if you're lucky, you understand the error message. Well, usually, once you understand the error message. It should be the other way around, but that's a different thing. And that's not a complaint. It's very tricky to do that right. The problem is, in this code, we call insert, and that insert then fails to compile because of types that don't match. We cannot convert a constant to a const std set value type, aka a const std string. Okay, let's solve this problem. Let's add a concept. Again, we can use a standard concept that standard concept here says, well, there's an additional constraint for this function template, which is the type we insert has to be convertible to the value type of the collection. This does not change the fact that we either compile or compile not, but improves the error handling. So we check things not when we compile the body. In the call, in the function call, we say this has to be required. And the error message changes. So here's an example how this looks now in Clang. And instead of going into the deep darkness of SDL set line 518, we say, oh, you know what? There's a constraint not satisfied. I cannot call that. I don't find a matching function to call that. There's a constraint not satisfied because convertible to from an int to this value type evaluates to false. Awesome. Well, the messages look different. Some are very well readable. Clang is great with that. Visual C++ is good. GCC is pretty good. Let me say it that way. But of course, it always depends on the detailed use cases. Look at this once again. We have a requires clause again. And that requires clause combines two types. They check a relation between two types. The second template parameter type T, and using the first template parameter type, but with the helper function looking at the element type of this collection. Can we somehow use this as a direct constraint for template parameters or even for auto? Yes, we can. Even if it has multiple template parameters, we can apply them to one single template parameter, provided we pass all the others. So you see here in the declaration, we say, for a collection type which has to be arranged, we have another constraint, which is that type T is a type that is convertible to the value type of the collection. Nice. Very well readable. I like that. Good. So far, so good. The usual thing that I ask in trainings when I am at this point is a couple of things. One obvious question is, and what if I have two generic functions with two constraints and both are met? So here's one example. Let's introduce the concept has size. So we here simplified by saying we have a member function called size, and the result is convertible to an int. And then we have another concept that checks whether we support the index operator by saying, assume I have an object of this type, could I use the index operator passing the index 0? That's a little bit funny, because what you exactly specify here is not that you can only pass an int as an index. You could also pass a raw pointer as an index, because that's a valid 0. 0 is a valid pointer type. So to make it a little bit more strict, you might pass 7 or so, because that is an int. But that's probably not a problem in practice. But it tells you a little bit about the thinking when you specify concepts. Now let's introduce two overloads of function foo. One foo requires has size. Another foo requires has index operator. And now let's call this for list. So let's call foo for list object. Well, lists are containers that have a size member function but not an index operator. So that works fine. Only the first foo function is valid, and that will be called. If we now call a vector, pass a vector here, call foo for a vector, we have a problem. We have two foos that match, because foo has both index operator and size. So the compiler will say, that's ambiguous. I have no idea why to prefer one over the other. But you can solve that. So one is to say, let's specify one foo has size and the index operator. This, again, is a special case of the first definition of foo. So we say has size and has index operator together. Subsume has size. So if you satisfy has size and has index operator, has size alone is always satisfied. So therefore, the second one is more special than the other, and it will be preferred if both foo could be called. But you could also do something like, I have a concept, has size and index operator, and if you have a foo for that, and a foo for has size, one is preferred over the other. So the second foo is more constrained than the first one, and doesn't create ambiguities. That is used a lot in the C++ standard library when specifying concepts. So you have seen the concept std ranges range, which more or less requires, can we iterate from begin to end with reasonable behavior and performance? We subsume from that. So we say an input range is a range with additional constraints. A forward range is an input range with additional constraints, and so on and so on. All these constraints are all these concepts are concepts to say, let me use a range to read the elements, to read the value of the elements. There are other range concepts like output range, which can be used to check whether you can write new values, assign new values to the existing elements. There's a range called, is it a sized range, which requires, can I ask the range for its size, and is that question cheap? The second one is, again, a semantic question, a performance question, a runtime question. Common range says, do begin and end have the same type, which is not always the case. And borrowed range asks, if I get an iterator, is the iterator independent from the lifetime of the range? Could I use the iterator even if I destroy the range I got this iterator from? So let's look at the first example. That subsumption hierarchy you saw here has the following effect. If you write two implementations of a function call, let's print every second element of a range, you have one implementation that is constrained for random access ranges, and another implementation that's constrained for input ranges. You see, the concept is directly applied to auto. Const is outside that. So if it's a random access range, you know that less than is supported and plus equals 2 is supported. So that's the way you can implement it. Let's iterate over the elements, always jump ahead 2 elements, and make sure we don't jump over the end, so we have to use less than to check against the end, which is not what we can do in general. In general, we can only use ++ and not equals or equals. So in the general case, we have to do something else. We have to say, well, let's always compare against the end. And to get to the next value, we have to increment the iterator and then check, is it at the end? And if not, increment it again. That's what this code does. That works with all ranges. The good thing, because we have subsumption, is that this works for a vector. Because for a vector, both print every second calls can be used. Because a vector satisfies the requirements of a random access range and satisfies the requirements of an input range. But because random access range subsumes random input range, the first one is preferred and used. While the second one is used for a list, because for a list, the first function template is not satisfied and cannot be used. And if you pass something that's not a range, like an int, then you get a qualified error message. I cannot compile, I cannot find a matching print every second function. There are two candidates, and in the first one, the concept random access range is not satisfied, and the second one, the concept random input range is not satisfied. Okay? Very powerful. By the way, please note that subsumptions are not checked in a way that we say, let's look exactly at the expression how a concept is defined. You cannot do this. You cannot say, let's have defined a concept that is a big type. Well, for me, big is size is greater than 8, but doesn't matter. And then we have a big class type, which is size of t is greater than 8, and the type is a class type. If you overload two functions, one using the one concept, one using the other concept, that's ambiguous. Because there is no check for subsumption except you're using concepts. So that's also a difference to compile-time Boolean values. Concepts allow subsumptions. Concepts allow to create hierarchies of satisfaction. That's an interesting sentence. Okay, so if you instead do this, big class type is big type plus an additional constraint. That works. Now we have a subsumption hierarchy. And this works not only directly, this works very indirectly. You could have something like a concept big R class and a concept big AND class, and that big AND class subsumes the concept big R class, because if both is met, one of them is met, the one or the other. And very indirectly, this can happen. Very indirectly, however, means that compilers have to create a syntax tree of all the concepts and what they subsume and what they subsume. So if you use a lot of OR expression especially, that can slow down your compile time, not the runtime. Okay. Now, I have to say here one thing about geometric objects and cowboys. What? Geometric objects and cowboys? Yeah. Because when we standardize this, the question came up, shouldn't we automatically subsume in a way that if something requires more than another, so if a set of requirements is a subset of another set of requirements, shouldn't this automatically subsume? Well, the counterexample was this. Why this was discussed in the standard committee. So think about you have a geometric object, a concept for geometric objects. Okay, this is a class circle. It has a draw function, and the concept requires that you have a draw member function you can call. Good, works. So the print we see on the top left can be called for this circle, because a print has a constraint, t must be a geometric object. And the constraint means I support draw. Now, let's introduce a concept called cowboy. I don't know how good your English is, but there's another meaning for draw, which is take the gun for cowboys. And that is, that's a way you can say, a cowboy calls draw, which is a totally different thing than draw for a circle. We agree on that. Well, most of the time, at least. Okay, so, and they have introduced a print function for cowboys. This does not automatically subsume. And that means that the call on the top right, the print call for a circle, because a circle also matches the concepts of cowboys, is ambiguous. By the way, here you see another reason why concepts should be coarse-grained, not check only for one member function. Draw is supported by geometric objects and cowboys, but I don't know, midpoint, probably not, or surface, whatsoever. Well, maybe it is, but that's a different thing. So you have to explicitly say that and specify subsumption. So you could say concept cowboy subsumes geometric object with some extensions, or you have a print saying this print is called if an object is both a cowboy and a geometric object. Then we have a solution. Good. That's the basics. And the only question left is, where can you use concepts? Well, concepts can be used wherever you have generic code. Generic code using template parameters or auto. So function templates, class templates, alias templates, that's generic type definitions, variable templates, that's generic variable declarations, and even non-type template parameters. The only exception is you cannot use a concept to specify a concept, to constrain the definition of a concept. I'm pretty sure sooner or later somebody will ask that as a new feature for C++ for some weird use cases. Two things I want to show you here. First of all, most examples, or maybe all examples I had so far, were function templates. So let's look at a class template. You could constrain this type T in some way. You could write here again, is integral, converts to int, is geometric object, whatsoever. But there's a very interesting special feature I want to show you with this class, which is you can constrain member functions. So this type, my type, always provides a function called print, which prints the value, and the value is of type T, which is a template parameter here. So my type double has a print that prints the double value. My type string has a print that prints the string value. You can specify member functions with a constraint applied to the class template parameter. So that way you can say, for example, I only have a member function is 0 if my type is either integral or floating point. These are two standard templates, standard concepts, sorry. So that means my type of double will compile if you call is 0, but for a string, which is neither integral nor floating point, this will not compile. So in the past, we had to use different function templates with partial specialization for that. That way, you can even switch between different return types on some constraints. And a very interesting feature is this. We use it a couple of times, which is my type has only empty if the pass type has empty. So that says, look at that. Empty is provided, there's a constraint, it's only provided if the value of type T has a valid member function called empty. And that is awesome. We do that in a lot of places in the standard C++ standard now. We say, okay, if the pass type has something we have something. We delegate that very easily, functions to the underlying type. Last example at the end, concepts for non-type template parameters. Here's an example for a non-type template parameter. I have a queue with a fixed size, so it's internally using a raw array. Yes, I should use std array, but just I was lazy. Okay. And then, we have an element type and we have a size. And that size is a template parameter. So you can create a queue of 5 int. Here you can apply a requirement, a constraint. You can say, well, max size has to be less than 10. And here's the definition of that. So in this case, you define a concept not applied to a template parameter that is a type name something. It's a constraint that applies to a value template parameter. So therefore, you have to use auto here in the declaration. So that means my queue of 10 ints and 0 ints will not compile, while with 5, it will compile. Very powerful, maybe not that compelling here, but look at this. We have compile time functions, like is prime. Is it a prime number? So we can specify that in a class, there's a requirement that the value you specify here as a non-type template parameter has to be a prime number. So C16 will not compile, C17 will compile. And you can do that using a concept. You can say there's a concept is prime, which says, okay, value has to be greater than 0, and by the use of the compile time function is prime, we check whether it's a prime number, and now we specify the requirement for the class as using this concept, and that has the same effect here. A lot of interesting things can be done with that, I'm pretty sure. That's it. Concepts, constrain, generic code to fix overload resolution and improve error handling. No code is generated. All is done at compile time to decide which part of my code to compile for certain types and values. Concepts are compile time Boolean values. You can use them, and that is special compared to a static const bool. You can especially use them to constrain template parameters and auto directly, and you can build hierarchies with subsumption. That's nothing ordinary compile time Boolean values can do. If you want to use that feature, use first the standard concept. They check a lot of corner cases and border use cases correctly. I didn't talk about that, but okay. If you define concepts yourself, do that with care. Prefer coarse-grained. Think about things like, should this work for references or not? And the way to specify that and to make sure that this is not broken and that people and programmers understand your definition of a concept, test concepts. You saw how to do that just with static asserts for all the different cases you want to support. That's it. Thank you very much. If you, by the way, in 2 weeks, I think, there's a meeting, C++, full-day training about concepts, rangeless. And if you are not so familiar with templates, the day before there is a template full-day training. So if you're interested, you're welcome to attend. That was the advertisement.
Thanks for the talk. Excellent summary. One question Something that came up repeatedly was, if I can do X, do X. Now, if the X is a bit longish, is there any way to prevent the repetition?
You mean the repetition that in the declaration you specify the things you again specify in the body?
Yeah, exactly.
Yeah, and the answer is the same as when this question came up about no except. Why can't we derive no except from the body of a function? Two reasons. First of all, we can separate the declaration from the implementation. And even with templates, that's possible. You need some tricks for that, but that's one benefit. The second is, it doesn't mean that if all my members do this and that, that just the summary of everything is the requirement of my code. Because in practice, when we program generic code, we know more constraints than just the things we do in the body. Things that might come later, things we know that could not happen, like do we have to check for NaN because we use floating point values? No, we know we never have NaN. So suddenly, your concept should even work there. So, and the third reason is you make your signature dependent on the body. The moment you change the body, you have to change the signature. And that is not what we call encapsulation. So these three reasons lead to the fact that we think, no, normally, it might be similar in pretty simple cases, but normally the granularity we check in signatures is different from the body and how it looks like. Does it answer your question?
Yeah, mostly. Not entirely happy, but I can maybe get back to you.
Nobody is happy with that answer, I know. Because everybody wants to generate it.
Thanks for the talk. I think I see a huge potential for increasing the code readability and also the performance optimization.
Good.
So I'm not having a question, but an idea. Continuing with the last presentation about the pipeline, I just came up with an idea that instead of going all the way to the end of the pipeline, we can actually implement some concept of handling all of these error cases, so we get an early return. Instead of going to end of the pipeline, and we only accept the continue procedure when there's no error appearing during the process. I'm not sure if you heard that presentation.
I did not, but I can say your general warning about things like that, which is never forget concept check at compile time. Mm-hmm. So anything that might behave differently because of the concrete situation at runtime cannot be checked with concept, at least not formally checked. You can only document it. So there are limits what you can do with concepts.
I see.
Yeah.
But definitely worth some exploration.
Well, and we use concepts when we use the pipeline operators to support views and types of views. We use them already, yeah. Tremendously, by the way. Views and ranges are the big library using concepts each and everywhere.
Great, thank you.
Thank you. Thank you very much.